So, all right, everyone. So, welcome back, guys. In previous session, so we explored Spark operations and looked at how data flow through the systems. And this naturally leads us to today's discussion, guys. Okay, and also this is the last session. So, in big data systems. And yeah, here in today's session, so we are discussing about the word of streaming and performance inside this Spark. So here's a simple question to get we started. So what happens when data never stops coming? Okay. I hope my screen is visible to everyone. Is it visible, guys? So I did not ask this. Is this visible to everyone? How about my voice? Is it clear? Can someone? Okay. So I was asking you the question, right? What happens when data never stops coming? What will happen, guys? Good evening. I started my class. So system get full. Okay. So data might loss. So these are all the answers I'm getting from your end. Okay. Guys, we are now moving from batch oriented thinking into the reality of modern systems where data is continuous. So the best example for that is where you're going to get continuous data, your social media feeds, IoT sensors, server logs. Correct? No? See, our focus today will be understanding how Spark handles such non-stop data. So how it provides fault tolerance and how to optimize performance when working with machine learning and streaming workloads. So think of today as connecting the dots across everything we learned so far. Okay, but with the lens of real time. Okay. Yes, yeah, to warm up. So tell me in the chat using single word, guys. So where have you personally seen streaming data? So maybe in your job or daily life. Logs, okay. I started getting answers. Only on logs. Application logs, it is already texted by one of your friend. Online games, okay. Okay, stock market, IT tickets, okay, live streaming of cricket match. Very good answer. Kafka stream is not. So videos from where? So videos from YouTube. Correct, no? And click streams. Exactly, guys. So streaming is everywhere. So streaming is everywhere. Correct, no? Okay, guys, today. So since we are diving into Spark streaming world, it helps to know where we are headed. So here is a quick framing questions. So what are the three pillars of real-time big data processing? What are the three pillars, guys? These are the three pillars, right? Stream processing. This is the first pillar. So here we try to understand what it, understanding what it means at a system level. So that is stream processing. And what is the second one? The second pillar is Spark streaming. So how Spark itself supports real-time workloads. And finally, we have the last one. So that is your Spark performance. So how to keep everything running efficiently. So think of today's content as having two layers, guys. So first one, I'm talking this as conceptual layer. So first layer, I'm calling it as conceptual layer. So how streaming systems are designed. And the second one, I'm taking one more layer, that is Spark specific layer. So these two layers I'm considering here in today's session. Okay. So now quick thumbs up or thumbs down. So have you worked with any streaming tool before? Have you worked with any streaming tool before? Kafka, Flume, Spark, Spark streaming, or even AWS Kinesis. So can you all type on chat box? Or you can give me, yeah, Spark. Many of them are worked under Spark. No, okay. Many of them are saying no. Very good. Not an issue, guys. Okay. Okay. So maximum students have said Spark. Okay. Now I'm jumping into the very important concept, that is streaming data systems. Guys, streaming data systems are not a single monolithic application. So they are layered architectures made up of loosely coupled components. Correct? No? It is made up of loosely coupled components. Imagine, okay, imagine a relay race. So each runner handles a segment independently, but together they complete the race. Correct? No? So these systems do three important things, guys. So what are the three important things? The very first one, see here, the very first one is listed. So they maintain high availability. So if one system fails, others keeps going. And they help manage complexity by separating responsibilities. Okay, collection, flow, processing, storage, so on and so forth. And they keep cost under control. Guys, each component can scale independently. So also along with that, one more thing you have to notice, guys. So one more thing is flexibility. Okay. So all component may live on separate servers, or multiple components may be co-hosted. And not every system needs every component. So it depends on the use case, guys. Okay. See here, I'm not showing you any diagram. Okay. So, but mentally picture a pipeline. So data entering from the left, so flowing through processing unit and then reaching storage or dashboard on the right hand side. So this imagination you have to what? Think, guys. Okay. So here in one word, so let me see how many of them are going to give right answer to this. Give me an answer in one word, guys. So what do you think is the most important property of a streaming system? Is it speed, reliability, or scalability? So I want you people to type your message and the message in the chat box. Reliability, okay. Scalability, I'm getting mixture of answers. Speed, at most, okay. Okay, so I think reliability is the correct answers, guys. Okay, so now that we understand the big picture, let's break this architecture down into its component. So now look at here. Next slide, I'm showing you the components of architecture. You all look at here. Since streaming systems are layered, the natural question is, so what are these layers? Correct? No? Guys, this slide gives you the 5 logical components that appear in most streaming architecture. So what is the first one, guys? First one is collection. Okay, let me number it as 1. So first one is collection. So here in this phase. Okay, in this phase, raw data is captured. Okay, second one is data flow. So here in this phase, moves data reliably between systems. And third phase is processing. So here where analytics or transformations happen. And fourth one is storage. It is nothing but for persisting or caching results. And finally, we have delivery. Okay, so here we are sending processed output to users or downstream the application. So think of it like an assembly line, guys. So sensors collects the data and conveyor belts move it and machines process it. So warehouse stores it and delivery trucks send results out. Okay, so you will see in later slides that Spark fits mainly in the processing tier, but it interact with all other layers. Okay, that you should understand. So now I'm showing you one more diagram. So now I'm going to show you the visualization of architecture with a generalized view. Okay, you all can observe now. Okay, guys, now we know the components, right? Now let's see how they connect with each other. So here the framing question, guys. How does data actually travel from injections to visualization? Correct, no? Guys, this slide shows a generalized streaming architecture. So let me describe what you are seeing here. See, on the left-hand side, so this is the first phase, right? You have collection sources. Okay, you have collection sources. Look at here. So maybe from weblog, you are going to get data. So IoT, you are going to get data. Mobile events, you are going to get data. And these feed into flow tier. Okay, so think of Kafka or think of Kinesis. So that acting like a what? Buffer, correct? No. Are you all getting my point? See, this is very, very important. You have to understand, guys. And next one above that. So sit the word processing engine. Okay, so processing engine means what, guys? So we have Spark streaming, Storm, Flink. So which keeps transforming data continuously. And after that, what we'll be having, guys? So we'll be having storage system. So example for storage system, can anyone tell? What are the example for storage system? So I can take the example of HBase, Cassandra, or in-memory stores. And finally, what is the last one, guys? So finally, I'll be having delivery layer. So delivery layers are nothing but, see here, I have a delivery tier. So delivery tier or delivery layers are nothing but dashboards, alerts, or mobile interfaces. So the important idea here is this. So each component is specialized, and by separating duties, so we get scalability and also reliability. Okay, so now let's do a quick poll. Let me see how many of them going to give correct answer. So if you had to insert a machine learning model into this diagram, so which tier would it belongs to? Yeah, look at the diagram now. So now we are planning to insert machine learning model into this diagram. So which tier would it belongs to, guys? Let me see. Analysis tier. Okay. Okay. So many of them are saying analysis. Analysis is nothing but what, guys? Processing tier. Analysis, processing. So both are same, right? Your answer is perfectly correct. So analysis tier is the correct answer. But storage also plays a role when models need persistence. So that you should understand. Clear? Okay. So now I'm jumping into next slide. Guys, now that so we have seen the overall architecture. Now let's zoom in and start examining each component. Okay, and here is a simple questions to frame this slide, guys. So how does data actually enters a streaming system? Guys, this slide is mainly focuses on the collection systems. Okay, collection systems, and the very first entry point of streaming data. So in the early days of the internet, so websites generated log data in the standard W3 W3 standard, correct? No, W3C format. So simple text logs recording every click. But today, system use richer formats like JSON, Avro, and Thrift. Correct? No. So making it easier to store more structured and schema information. Guys, the actual data captures happen at edge server. I think you're all aware of this, right? And these, see, what do you mean by edge servers? Guys, edge servers placed close to the user or device to collect events quickly. Okay, so new servers usually integrate directly with the modern data flow systems like Kafka. So while older servers may not have such capability, then what is the key point you have to understand here, guys? It means the collection process is highly application specific. A social media app collects user interactions. So whereas an IoT platform collects sensor readings. Guys, the collection layer must adopt to these domain needs. That is very, very important. Okay, and see, this slide is, see, you one more thing, guys. One more thing. So, okay, before that, let me ask you one question, guys. So can you all name any one format? Let me go with the chat box. So can you name one format you have worked with or heard of? JSON, Avro, Thrift, CSV, anything? Anything guys? JSON, okay. Tune, okay. This is first time I'm hearing about Tune. Okay, JSON is one format, CSV is the another format. And okay, so three members have typed JSON. So JSON is dominating here. No surprise, right? So it is the de facto standard today, is it? Yeah, Parquet, very good. Okay, fine. Guys, once we collect the data, the next stage is getting it reliably from the edge to the processing engine. So that's where the data flow tier comes in. Okay, so now I'm jumping into the second layer that is called as data flow tier. So before we move to the what next tier, so let's deepen our understanding of the collection system with this simple question. What happens when the collection tier is faster than the processing tier? Valid question, right? Guys, real world systems rarely operate at the same speed. The collection tier might generate thousands of events per second, while the processing tier can handle only a portion of that, guys. So this mismatch is why we must separate the collection tiers from the processing tier. I think now you all get correct idea. So why we have to separate it. So without that separation, the entire system can get overwhelmed and leading to dropped messages or bottleneck. So to solve this, guys, so we place one more layer. So that layer is called as intermediate layer. Look at here. So we are introducing one more layer. That layer is called as intermediate layer. So can anyone tell me? So any intermediate layer you are aware of? Any intermediate layer? Yes, can anyone? So those who are good at Spark. Kafka. Would you agree with my point? Usually Kafka like message queue. Correct. Correct. Yes. Correct. No. See, guys, this Kafka, see, Kafka like message queue which buffer incoming events. So this layer accepts messages from the producers and ensure they are delivered to the processing layer. So this intermediate layer So this intermediate layer provides the at least once semantic. So that at least once semantic is also called as, okay. So this is at least once semantic, guys. Okay, semantics actually. So you will never lose data even if something fails somewhere in the pipeline. Understanding my point, guys? And now that, see, now that data has safely entered the system and is buffered. Now let's move to the heart of the pipeline. What is the heart of the pipeline? The processing tier. So next line, I'm jumping into the processing tier or analytic tiers. Okay. So now that we have collected data and separated out the what buffered layer. Correct? No. Now my question is, the next question is, so how do we move data reliably between components? Guys, this slide emphasizes the rate mismatch problem. See, the collection system may generate data faster than the processing system that can consume it, or the reverse may happen. So that's why we need what, guys? So that's why we need data flow tier. So data flow tier is required. So typically this is implemented using Kafka or Kinesis, guys. So this tier acts like a shock absorber, guys. So it receives events at high speed and stores them until the processing layer is ready. And it also provides real-time interface. Okay, it also provides a real-time interface for both data producers and also consumers. Okay, so last slide I've shown you, right? At least once. So the at least one semantics guarantees that every message is processed. So even if it means duplicates. So processing frameworks then take responsibilities for handling duplicates. Okay. Now I'm jumping into the what next layer, guys? That is processing or analytic layer. Okay. You just look at here. So now that the data has made its way to the processing engine, the question becomes, how do we process massive streams efficiently? So guys, this tiers operates on the principle of data locality. Try to understand this. So this is working on data locality principle. So instead of moving data to the code, we move the code to where the data lives. So frameworks like Apache Kafka, Storm, and Kafka streams distribute computations across multiple nodes. And they take care of partitioning, scheduling, and managing jobs. The developer simply writes high-level logic. That's all. So this tier is where all real-time analytics happens, guys. Transformations, aggregations, joins, anomaly detection, so on and so forth. Everything will be happening here only. The big value here is that the framework handles the complexity. The meaning of this is you no need to manually manage threads. So cluster communications are fault recovery, guys. Okay, so it will be what done by itself only. So now, guys, so after this processing tier, so we have storage tier. So we have processed the data. So now the big question is, so where do we keep the result? Correct? No, guys, storage in streaming systems varies depending on the use cases. Guys, most streaming results are used only once. So often we store them in memory for fast access. But for some scenarios like fraud detections or historical analysis, we need to store the process data permanently. So this is where, guys, this is where this NoSQL like MongoDB and Cassandra comes in. Okay, they can ingest large volume of data quickly, scale horizontally, and handle varied data format. So however, guys, this is important. So there is no single database that fits all streaming use cases. See, your choice depends on whether you need high write throughput or strong consistency, flexible schema, or fast read performance. So based on that, you are going to choose the tool actually. Okay, so you just imagine this tire as a warehouse. So sometimes you need temporary bins and other times you need long-term cold storage. Correct? No. So now I have a question to you all, guys. I have a quick question to you all. So let me see how many of them are going to give a correct answer. So if your streaming system outputs 10,000 events per second, I'm repeating the question. If your streaming system outputs 10,000 events per second, so which storage would you prefer? Would you prefer SQL or no SQL? Just type your answer. No SQL. Nodal. Ravi Kumar has typed Nodal. It is no SQL, right? No SQL. Okay. So maximum answers, I'm getting no SQL. Answer is correct, guys. So no SQL dominates because it can write at extremely high speed. Okay. So now, guys, the data is stored. Now we have to understand how do we present it to the end users or other applications. So that's our next component. What is the last component? The last component is delivery layer. Okay. So here the question is, the next questions becomes, so how do we bring these insights to the people or systems who need them? Okay, the delivery layer is where processed information becomes visible and also useful. Guys, today delivery systems are no longer limited to desktop dashboards. So we are seeing a rapid shift towards mobile interfaces. I think everyone will agree with my point. So lightweight web dashboards. Correct, no? Lightweight web dashboards. And along with that, live updates. So we are giving live updates. See, most real-time visualizations use the combination of HTML, CSS, JavaScript. Along with that, what we are going to use, guys, we are going to use WebSockets for instant updates. And we are going to use SVG. Okay, we are going to use HTML5. What canvas to render visual charts, gauges or maps. Correct? No. So this is also the layer responsible for triggering alerts. Okay. So think of fraud alerts, system warning or anomaly notification. Guys, the key insight here is delivery is not only about showing data to humans. So sometimes, so this layer sends data to downstream applications, APIs and microservice that depends on the streaming output. Okay, so now I want you people to imagine a dashboard that continuously updates. So like a heart monitor showing a live heartbeat signals. So that's exactly what streaming delivery layers enables. Okay, so now can anyone tell me? So can anyone type me one tool or one framework you have used for visualization? Which tool you have used for visualization, guys? Let me see. Anybody is used tool for visualization? Power BI, Tableau, Quick, okay, Click View, very good. Grafana, very good. Power BI is repeating. Correct, no? So we have so many tools, right? Nice, a good mix of what? Grafana, Power BI, Tableau, so many answers I'm getting. Perfect answers, guys. So now that we have broken down all the architectural layers, so now let's zoom into a fundamental model used in stream processing. That fundamental model is called as the continuous operator model. So let me look at the next slide, that is continuous operator model. Guys, the continuous operator model is one of the simplest way to think about stream processing. Okay, so here I'm giving you some basic idea, guys. So here I'm giving you some basic idea. You have to understand this. Guys, data flows into the system continuously from injection tools like Kafka, correct, no? Or Kinesis, or you can use Flume, so on and so forth. And each piece of data, so each piece of data means what? Each event is processed as soon as it arrives, rather than waiting to form a batch file. I think everyone will agree with my point. And the cluster contains multiple worker nodes. So any cluster, you take any clusters, guys. So that will be containing multiple worker nodes, and each nodes runs one or more operators continually. Correct, no? Then what about this source operators? Guys, a source operators always receives the data. And what about sync operators? What is the job of sync operator? A sync operator sends process data outward to systems such as Cassandra, or it will send data to what? HBase. Otherwise, sometime it will send data back to the Kafka. Okay, so this magic is that each operator handles data one record at a time. So one record at a time. Okay, so almost like a factory workers picking up items of a conveyor belt. Okay, so you can see this diagram. So this diagram, what it is showing, guys, it is likely show a pipeline. Correct? No. See source. This is source operator feeding workers. This is feeding to the workers. And sync operators. Next we have sync operators here. So that is outputting the result. See, all connected in a continuous flow. Correct? No. See, all connected in a continuous flow. Guys, now I have a quick questions on chat box. So let me see how many of you are going to give a correct answer. So do you think this model can automatically recover from failures? Say yes or no. Say yes or no, guys. Guys, you have to remember your answers lead directly to the challenges of this model. Correct? No? So once it is no, your answer leads directly to the challenges of this model. So now, see, now that we know how continuous operators work, so let's look at the limitations of this approach. What are the limitations of this approach? See, next slide, I'm giving you the limitations, or we can call it as challenges. Guys, see here, I'm highlighting the major pain points. So the very first point I'm giving here is fast failure and straggler recovery. Guys, operators are permanently assigned to nodes. So if a machine slows down or fails, so recovery is difficult. Correct? No? Why recovery is difficult? Because the system is not designed for dynamic reallocation. Okay, so this is designed for what? Static allocation, not dynamic reallocation. So this is one challenge actually. And the second challenge is load balancing problem. Correct? No? If some operators gets more data than others, the imbalance creates bottleneck. So guys, unlike Spark's dynamic scheduling, continuous operator system struggles to rebalance on the fly. And the third disadvantage of using this is lack of unified processing, unification of streaming, batch, and interaction workload. Guys, many workloads need to combine streaming with batch queries or ad hoc SQL queries. So continuous operator system are not designed for this hybrid use case. That you should remember. And finally, we have one more challenge here. So that is related to the machine learning concept. So advanced analytics with machine learning and SQL queries. Or we can call it as advanced analytics also. Guys, modern applications requires live model updates or interaction queries on the what streaming data. Correct? No. But continuous operator engines don't have a unified abstractions to support machine learning or SQL and streaming in one place actually. So this is exactly why systems like Spark streamings are so valuable. So they overcome many of these shortcomings, guys. Okay, so seeing these challenges, so make it clear why Spark streaming was designed the way it is. So let's return today to the topic list for the what moment. See here. So now I'm jumping into next slide. Okay. So which topic I have to take next, guys? So I have to start with Spark streaming now. I think till here everything is clear. Stream processing is completely clear to everyone. Shall I get crystal clear message and chat box once it is clear? Shall I get CC message and chat box? So once it is clear to each and everyone. Okay. So now I'm jumping into the next part. Guys, given the challenges of continuous operator models, the natural question is, what makes Spark streaming a better alternatives? Correct, no? Guys, there are several compelling reasons. Okay, there are several compelling reasons. Look at here. See, the very first one is fast recovery. Fast recovery. Guys, what we are using in Spark? Guys, in Spark, we are using RDD. Correct, no? In Spark, we are using RDD. So Spark's RDD lineage enables extremely quick recovery from failures and also stragglers. And the second one is better load balancing and resource usage. Guys, Spark dynamically schedules tasks for each micro batch and letting it adapt to workload variations. Understanding my point, guys? And the third very, very important point is unification. Okay, so this is the what big win, guys. So this is the big win in what Spark concept. Guys, Spark combines streaming, okay, batch and interactive analytics in a single engine. Is it not good, guys? So it is combining streaming, interactive, and also batch. Is it not the advantage, guys? So everything we have combined in a what single machine. So you could join streaming data with a data frame. So run SQL queries, apply machine learning models. So all in the what same program. All in the same program. And one more advantage of using this is developer productivity. So what do you mean by developer productivity, guys? What do you mean by developer productivity means? Guys, the same API you use for RDD, the same API you can use for data frames. See, all these work for streaming, guys. The meaning of this is fewer tools to learn here. You're not supposed to learn more tools actually. Fewer tools are enough. And the last one, the last very, very important point is integration. Guys, a Spark integrates natively with MLlib. Okay, that is the advanced libraries, MLlib, graphics, Spark SQL, and many other ecosystem tools. Guys, in short, Spark streaming inherits the strength of Spark, speed, fault tolerance, and unified analytics and applied them to live data. Now I have a quick question to you all, guys. Let me see how many of them are going to give a correct answer to this question. So what do you think is Spark streaming biggest advantage? What is the Spark streaming biggest advantage, guys? Okay, DAG. Fault tolerant. Very good. Fault tolerance is the correct answer. Now, just now I've discussed, right? Speed, unification. Correct, no? See, unification is the game changer here, guys. Okay, so now that we know why Spark streaming matters, now let's explore how it actually works. Okay, so next slide, I'm showing you how it actually works. Look at the overview here. Look at here, guys, everyone. See, now that we know why Spark streaming exists, the next question is, what exactly does Spark streaming let us do? Guys, this slide gives a high level view of Spark streaming. Okay, see, Spark streaming is an extension of core Spark API. So which means you already know most of the what foundations, right? So the same idea here. So we are using RDD concept, we are using transformations concept, cluster and task concept. So applying streaming as well. Okay, and Spark streaming does three big things, guys. What are those? The very first thing is, look at here. These are the three big things. The very first thing is data can be ingested. So ingest data from streaming sources like Kafka, Flume, Kinesis or TCP sockets. So this is the first one. And second one, process. See, it is processes the data using familiar operations like mapper, reducer, join, and windowing. And along with that, the third one is push results out. Which result is it is pushing out, guys? The processed data or processed result are pushed out to the dashboard, are pushed out to the file system, databases. Correct, no? Or live applications. You can push the same data to the live applications. The final point is very, very powerful, guys. You have to look at this point actually. Okay, so because it is still Spark under the hood, you can mix the streaming with SQL queries, machine learning model, or graphic analytics. So your real-time pipeline becomes extremely flexible here. Correct, no? It is extremely flexible, guys. So now, what is the most common streaming source you have seen in a real project? So maybe you have seen Kafka. So you have seen files, sockets. So many answers, right? So the best answer always would be Kafka. Okay. Guys, to understand Spark streaming design, we need to learn its core abstraction. That core abstraction is called as discretized streams, or we can call it as D streams. Or we can call it as, in short form, we are going to call it as D stream. Okay, guys, this is where Spark secret sauce comes in. So that is called as micro batching. So we can name it as micro batching. Let me write here. We can name it as micro batching. Guys, Spark divides the incoming live stream into small time-based batches. Understand this. Are you all understanding, guys? And each batch, so each batch is becoming what, guys? So each batch is becoming RDD. And Spark processes these RDD using normal batch engine. Is it not interesting, guys? And when these batches are processed one after another in very small intervals, you get the illusion of real-time processing. So how many of them are finding this is very interesting? Is it interesting? Is it interesting, guys? What Spark is doing? Spark is dividing incoming live stream into small pieces. So that is called as batches. And each batches becomes an RDD. And each RDD is executing like a what normal batch engine. And these batches are processed one after another in a what small intervals. So this solution is what looking like real-time processing. The abstraction that represents this logical continuous stream is called as D stream. So how many of them understood D stream concept clearly? So how many of them understood, guys, D stream concept clearly? Is this clear? Yes or no? See, guys, D streams essentially a continuous streams of data. So it is essentially a continuous streams of data. So this is viewed by the user as a single entity, but it is implemented internally as a sequence of RDD. Internally, it is represented as a sequence of RDD. So that's why Spark can easily support operations like joins, maps, and windowing. So it is just doing them on RDDs. And this diagram is completely giving you the idea. Correct? No. See, you will see D streams here. D streams drawn as a line made up of small blocks. See, these small blocks I'm talking about. And each block is one RDD, illustrating how Spark breaks down time into discrete pieces. Okay, so your batch or streaming behaves like, see, your batch file or streaming file, that is behaves like what streaming, but internally it is a batch based. So this is the great insight you are getting from this explanation. And since micro batching is so central, so let's look at why batching is beneficial. So next slide is explaining you the same thing. So benefits of batching. See, now that we know Spark divides data into batches, the question is, why is this beneficial? Guys, this slide highlights two major advantages. So the very first one is, this is the point. So faster recovery. Look at here, everyone. So guys, because each batch becomes an RDD, Spark uses RDD lineage for failure recovery. So if a worker dies, the batch can be recomputed from its parents. So just like any other Spark job. Understanding my point, guys? So if anything is failed, then what it is going to do, guys? So it is recomputed from its parent. So this is one advantage. And the second advantage of this is better load balancing. Okay, better load balancing. Guys, Spark does not assign long running operators to fixed nodes like continuous operator systems. So instead, every batch gets scheduled dynamically. The meaning of this is Spark can distribute work across the cluster based on real-time load. So this dynamic batching or dynamic scheduling is one of the reasons Spark streaming scales very elegantly. Understanding my point, guys? So then tell me in one word, what is the biggest advantage of micro batching? What is the biggest advantage of micro batching? Can anyone answer? Recovery or load balancing? Recovery or load balancing? I'm asking you, Ajit. It is recovery, right? Recovery, right? How come load balancing? See, the recovery is the core strength of RDD model. Am I right or wrong? Okay, fine. Guys, but there is more, guys. So batching also connects streaming to Spark's batch and also SQL layers. So here I'm continuing with the second one. You can look at here. So one of the Spark biggest superpower is the ability to blend streaming, batch, and interactive analysis. Correct? No, interactive workloads. Because a D stream is just a sequence of RDDs. So you can do things like join streaming. See, you can do things like join streaming. See, here I've taken the example. So join streaming data with the static RDD and convert dstream into data frames and run SQL queries. Okay, you convert it into what data frames and then run like what SQL queries. So you can apply machine learning algorithms. Okay, so machine learning library models to each RDD. Okay, such as running k-means predictions or k-means predictions on what? See, streaming data. So this kind of compensability is extremely rare in streaming engine. So let me take one small example, guys. So imagine you have a static customer database and a stream of transactions. You can enrich the stream by joining both. So something extremely hard in continuous operators engines. Okay, so now think fast, guys. So would you rather enrich your stream using SQL or using join API? SQL or join API? So almost SQL, right? So SQL. So that's the beauty of Spark Unified API, guys. Understanding? See, now that, so we understood the conceptual strength of batching. So let's look at how Spark gets data into D streams through sources and receivers. Okay, this is the next slide. Guys, now that we know what D streams are, and the next big question is, how does data actually, sorry guys, how does data actually enters Spark streaming? Guys, this slide completely explains the concept of receivers. Okay, so every input data stream, see, I'm talking about every input data stream I mentioned here. Okay, except your file stream. See, except your file stream is connected to receiver object. And a receiver is responsible for taking data from a source or storing it in a Spark memory with replication. I think now you're all getting right. What is the main responsibility of it? Guys, there are two categories of sources. So we have the first one is called as basic sources. See, these sources, basic sources are built directly into the streaming context API. Streaming context API. So example for this is file system or socket connections. And these are easy to use, but so these meant mostly for what simple demos or initial startups, initial setups. Okay, then what about the second resource? The second source is called as advanced one. So this is the first one and this is the second one, that is advanced sources. Guys, these includes Kafka, Flume, Kinesis. So these are all available through extra utility classes. Okay, they require linking additional libraries and provide more robust streaming support. Okay, guys, here we have one more what comparison here, or one more comparison we have in between reliable receiver and also unreliable receivers actually. Guys, reliable receivers acknowledges receipt only after the data is stored in a Spark. But what about unreliable receivers? Guys, unreliable receivers does not send acknowledgement. So data loss is possible in case of this unreliable receivers. Guys, in real production system, reliable receivers are always preferred. Okay, you just picture the receivers as the what front door of your Spark streaming. So catching data as it arrives and placing it into memory safely. So that is receiver, guys. Okay, so now guys, see, now that we understand how data enters the Spark streaming. So now let's move on to what we can actually do with the data streams. So starting with transformations. See, I'm starting with transformations here. Transformations operations. You all can observe here. Guys, this slide is completely introducing the idea of transformations on D streams. Okay, just like RDD, So D streams support a wide variety of operations to modify or analyze incoming data. Okay, the goal is not memorize every operations, but to understand that these streams behave very similar to RDD. Guys, they allow filtering, mapping, reducing, joining, windowing, and so on and so forth. Okay, so think of it in this way, guys. A D stream is like conveyor belt carrying small batches of data. Then what is transformations? So transformations let you decide what to do with each batch, whether I have to clean it or aggregate it or correlate it with another string or enrich it with static data. So that is the job of transformations. Understanding my point, guys? So you just imagine, guys, the diagram. The diagram from this Spark documentations typically shows D streams flowing through transformation boxes like mapper, reducer, join. So why it is required to produce a new data stream? So very simple. So that is required to produce a new stream. And here we have mentioned, guys, mapper, flat map, this and all already have explained you. The same thing I've given with the meaning here. So you just go through all these meanings later. Okay, now that we know transformation exists, so let's see a visual list of commonly used ones. See, these are all commonly used ones. Output operations. Okay, before this, so this, should I explain this, guys? I know what, I think you people are knowing about this, right? Yes or no? Should I explain this functions, each and every functions in detail? You want me to explain it in details, guys? Quickly paste a message and chat box. It is not required, right? So mapper. So this is like what element wise operations. So this is familiar, right? Already it is familiar. I don't want to explain this concept again, guys. Okay, now I'm directly jumping into output operations. Guys, just now we have talked about transformations. So the next question is, how do we send processed result to the outside world? That is called as output operations. Correct? No. So this slide shift to output operations. So which allow D streams to write results to external systems like databases, files, or dashboards. Guys, output operations are crucial because D stream do not store data by default. They must be pushed outward. So then what is common output operations here? The common output operations are, the very first one is print. Okay, so why you are going to use print, guys? So this is mainly used for debugging and prints the first few records, means then you can use this, right? So that is print. And the second one, you can use save as text files. Guys, see, you go with word count program with respect to your Spark. So once you have done with word count, so finally you have to store result in what? Files, right? So on that time you are going to use this function. So this save as text file is used to store each RDD in directory. And we have third one, save as object files. So it is almost similar. So similar to what? Object as text file. Okay, so next we have save as Hadoop files. So this is also almost same. So here we are storing everything inside the Hadoop system. That's it. And we have the last one, that is for each RDD. Guys, the most powerful option is for each RDD. So it is letting you to write custom logic to push RDD data anywhere. So either you can shift this to Kafka or shift it to databases, HBase, wherever you want. Guys, for each RDD is the workhorse of Spark streaming output because it gives you full control to integrate with any custom links, any custom sync. Okay. Understanding? So now I have a one quick question to you all, guys. So based on this slide, I have a one quick questions to you all. So which output operations do you think is most flexible? Which one is most flexible, guys? Print, save as text files, or for each RDD? Which one is most flexible? For each RDD, right? Why for each RDD? Because it is giving you the what? Complete control. Okay, thank you all guys. So just now we have seen transformations and output, but streaming gets more interesting when we look across time. And that brings us to what? Windowing operations. So now I'm talking about window operations. Guys, now that, so we have talked about single batch transformations. Now the question becomes, how do we analyze patterns that span multiple batches? So this is where window operations comes in. Guys, a window operation, let us look at data across a sliding period. So three important concepts here, guys. What are the three important concepts? The very first concept is called as batch interval. Okay, batch interval. So this is the frequency at which Spark creates a new RDD. For example, every 1 second or every 5 seconds, so it is going to create a new RDD. Understanding? And the second one is window size. Guys, this determines how much data is included in a window. How much data will be in RDD before processing. Okay. See, for example, if the window size is 3 batches, you just imagine. If the window size is 3 batches, so Spark uses the last 3 RDD for the calculation. Then what is the last one, guys? The last one is called as sliding interval. So this defines how often the window moves. So if the sliding interval is 2 batches, the window shift forward by 2 batches at a time. Okay, and one more thing, guys. Actually, windowing allows the task like count event over last 1 minute, compute average over last 5 batches, and detect trends over rolling time windows, everything. Okay, and look at this diagram. So this diagram shows 3 RDD, correct? No. 3 RDD being collected into a single window and then sliding forward while forming the next window. Clear? So are you all understanding, guys? Now let us look at the one more diagram to reinforce this concept. Okay, so see here, everyone. So we have introduced windowing, but the question is, what does a windowing computations look like visually? Guys, this slide is offering a more detailed visual of how windows slide over time. So you can imagine stream as a timeline divided into equal sized blocks. Okay, equal sized blocks. So we are going to call it as batches. And the window sits on top of this timeline and covers multiple blocks at once. Okay, so this mechanism always enables rolling aggregations like moving averages, real-time trending, or anomaly detections. Okay, see this diagram likely shows a highlighted rectangular windows moving across a sequence of batch blocks. A perfect visual for how Spark uses time-based grouping. So this is the example, guys, that you should understand. Okay, so here I've listed few Windows operations. You better go with this, guys. So all the Windows operations I have mentioned here, you just go with this. So I'm not going to explain this. I'm skipping this. Guys, now I'm shifting into the next very concept. Guys, now that we understand classic Spark streaming with dstream. So let's shift to the modern approach. And here the question to frame this slide, guys. What if streaming could behave exactly like SQL on continuous data? Guys, structured streaming takes streaming to the next level. So unlike D-stream, so which rely on micro batches, batched RDD, and structured streaming works entirely on data frames and also data set. So this is works on data sets or data frames. The meaning of this is your operations look like standard queries. Standard queries like what? Select, filter, or group by, aggregation, so on and so forth. Okay, so the key difference is structured streaming does not expose batching directly. Okay, so the meaning, see, you have to understand this, guys. Internally, Spark still uses micro batches. But as a user, you simply write queries and Spark handles the incrementally updating results. Because rows are much smaller units than RDD batches, structure streaming feels much closer to true real-time streaming. Understanding, guys? So this approach also brings tremendous advantages. So what are the advantages? So integration with Catalyst Optimizer, SQL support, so easier with ML, so easier with streaming pipelines, simplified code, everything. Okay, you just imagine, guys, your stream as an infinite table that keeps growing. Your query runs continuously on the table, updating results automatically. So that is called as structured streaming. Okay, I hope this is crystal clear to everyone. So that's all about the second part of your concept. So we have completed streaming concept. So now the big question becomes, so how do we make Spark run efficiently, especially under heavy workloads? Okay, guys, this slide. So this slide introduces the agenda to signals to shift into performance optimizations. Okay, so we are now entering the final part of the session, guys. So and also in this final part of the session, we are discussing shuffle operations, caching strategies, storage levels, along with that, machine learning performance considerations and hardware tuning. Okay, so this is the part of Spark that separates beginners from experts. See, understanding performance tuning gives you the ability to write efficient, cost-effective, and cluster-friendly code. Okay, so now let's start with one of the most critical one and expensive one. So that is the operation in Spark that is called as shuffle. Okay. Guys, to understand Spark performance, we must ask this question to everyone, guys. So why do some Spark jobs slow down drastically? The answer often lies in the shuffle concept. A shuffle occurs when Spark needs to redistribute data across partitions. So this happens when it needs all the values for a particular key in the same location. See, for example, they have given here. Okay, for example, you consider this RDD. So what it is considering? So 1, 2, 3, 4, and 3, 6. So when we apply this reduce by key on this particular RDD, okay, usually how we are going to write this? RDD dot reduce by key x comma y tends to x plus y. Guys, Spark must gather all the values for key 3 together. Okay, all the values for key 3 together actually. So it moves data between partitions. So sometimes even across machines. So this is slow because It involves what and all it is involving, guys? It is involving network transfer. Correct? No? It is involving disk spills. It is involving sorting, repartitioning. So the shuffle is one of the most expensive steps in Spark, guys. And understanding when it happens is crucial. Okay, so you just imagine or visualize partition sending arrows to each other, exchanging key value pairs like an all-to-all data exchanges. Okay, so now let us see how a reduce by key shuffle works step by step. So this slide is giving complete introduction on reduce by key. So let me show you here only, guys. Look at here. So we start with RDD. So this is the RDD I'm writing. I'm writing it separately. So I'm writing 1, 2, 3, 4, 3, 6. So this is the RDD I've written here. So the reduce by key operations groups value by key. That already I've told you, right? That already I've told you, right? What is key 1 here? So key 1 only value 2. Correct? No? What about key 3? What about key 3? Values, no, key 2 and key 3. So both I'm taking here. Values 4 and 6. So which must be combined, right? Which must be combined. So this is why Spark must rearrange data. So all 3, x pairs ends up together. So once grouped, Spark applies the reduce function. Okay. So reduce function, what is the functionality of reduce function? So it will add 4 plus 6 and it will give you the what? 10. Okay. So final output, what is the final output, guys? The final output is this, right? So 1, 2 and 3, 10 I'm getting here. So the important part is not the math. So it is the movement. So Spark had to pull together all values for each key. Okay. So now I have a question to you all, guys. So once you have understood this, so now I have a question to you all. So the question is, what triggers the shuffle? Addition or grouping? Hmm? Addition or grouping, guys? So grouping triggers the shuffle, right? Not the arithmetic, not the addition. That you should understand. Okay, so now let's generalize this beyond reduce key by. So what other operations cause shuffles? Okay, so here we have a generalizations. So we can call it as shuffle operations. See, conversation. See, this slide outlines the major shuffle triggers in Spark. One second, guys. So sorry, guys. Okay. So I was talking about this slide, right? Let me finish this. Guys, so the very first one I'm taking here is repartitioning. Okay, repartitioning. The very first point I'm considering here is repartitioning. Guys, operations like repartitioning and sometimes some function name is there. I'm not remembering that. Okay, let me take one. So that is repartitioning. That triggers shuffles because Spark must rearrange data into new partition boundaries. Understanding my point, guys? And we have the second one, that is by key operations. See, these are all by key operations. Reduce by key, group by key, and we have aggregate by key. See, all requires grouping. So which requires shuffling also. Okay. And we have one more, that is join operations. See, join operations like join. Let me write here. Join operations like join, co-group, join, or we can call it as left outer join, right outer join. See, almost always need shuffling so that matching keys end up in the what same place. Okay. And one more is all to all exchanges. So the next one is all to all exchanges. See, anytime Spark must see all the keys are recognized data globally or shuffle is required. Guys, shuffles are costly. They involve reading from all partitions, transferring data across executors, and writing temporary files. Understanding my point, guys? So this is the very, very important point you have to understand. You just imagine, guys, probably you are showing a web of arrows connecting partitions. A classic picture of all to all shuffles, right? Okay, I think you're all understanding. Guys, we have discussed shuffle now. Let's move to another performance pillar. So what is another performance pillar? That is called as caching and persisting RDDs. Okay, RDD persisting. We can call it as RDD persisting. Guys, we just examined shuffles and also we have declared. So shuffles are expensive. So the natural question now is, so how can we avoid recomputing things again and again? That will come to our mind, right? Guys, this slide introduces one of the Spark most powerful performance feature. So that is called as RDD persistence. And this is also called as, see, this is also called as caching, guys. Okay, so when Spark computes an RDD once, it normally discards it after the job finishes. That you should understand. Okay, but many workloads, especially ML, iterative algorithms, what these algorithms are going to do, guys, they are going to reuse the same data multiple times. So for that reason, so that will be happening by using some functions. What are those functions? The very first function is cache, or you can use persist functions. So by calling cache or persist, you instruct a Spark to keep the RDD in memory so that future actions on that data set run drastically faster. Understanding my point, guys? So some benefits includes here. What are those benefits? The very first benefits is 10 times or more speed ups for iterative algorithms. Correct, no? And no need to recompute lineage every time. No need to recompute. And faster interactive queries in notebooks. And this will always give you better performance when loops reference the same data set repeatedly. And most importantly, guys, Most importantly, what is the next one? Fault tolerance. Okay. So if a partition is lost, Spark simply recomputes it from the original transformations. Understanding? You just think of caching like pinning certain RDD blocks inside memory boxes across the cluster. So ready to be reused instantly, guys. Are you understanding? So cache uses the default memory only level, guys. That you should understand. Memory only level. So of course, caching is configurable. And that's exactly what the next slide explore. RDD storage level. See, now that we know caching exists, the question becomes, where exactly should Spark store the cache data? Guys, this slide explains that Spark offers multiple storage levels. Okay, not different storage levels, multiple storage levels. You can choose whether data is stored only in memory or in memory but serialized to save space, or on disk, or on replicated across nodes for faster recovery, or combinations of all this. Understanding, guys? And each cached RDD is associated with storage level. Each RDD is associated with this storage level object. So which you provide when you're calling this function, persist function. Okay. And cache is simply shortened for what, guys? Shortened for memory only. So choosing the right storage level will be always depends on memory availability, recomputation cost, fault tolerance needs, cluster size, and workloads. You just picture a hierarchy of storage options. So what you'll be having here? So memory, serialized memory, disk, and replicated memory. So you better imagine this. Guys, if your data set is very large but cheap to recompute, so then disk is fine when recomputation is cheap. Okay, that you should understand. So now let's learn how to choose the best level for a what given workload. Which storage level to choose? Which storage level to choose, guys? See, knowing the option is one thing, but the real question is, which storage level should you actually use in practice? Guys, this slide gives you a simple practical decision guide actually. The very first one, start with, so initially you have to start with memory only. Okay, if a RDD fits in memory comfortably, so this gives the best CPU performance. Okay, understanding? So if memory is tight, then use memory only service, memory only SCR. So this stores serialized objects. It is not service, serialized. Okay, so this stores serialized object. So saving space but costing some CPU to deserialize. And what is the third one? Avoid disk unless necessary. We all know the reason, right? So why we have to avoid disk, guys? Since disk is slower, only use it when recomputing the data set would be too expensive. Understanding? And what is the fourth one, guys? The fourth step is use replicated levels when you need fast failover. So this is useful in system serving real-time request. The last one is very much useful for real-time request. And one more thing, you look at this pointer. All storage levels provides full fault tolerance, but replicated ones avoid waiting for recomputations. Now you all tell me, guys. Now you all tell me. So which level is the most CPU efficient? Which level is the most CPU efficient? Memory only or memory only serialization? Huh? Which one is most efficient, guys? CPU efficient. So obviously it is memory only, right? Because memory only avoids serialization overhead. Correct? No. Okay. Guys, now that we know how to store RDDs, so let's see how to remove them when we no longer need them. So removing data. So guys, Spark manages cache data automatically using LRU. I think you have learned about LRU, right? Least recently used fashion. Okay, this is one of the algorithm or policy. So we are going to use in what? Spark actually. Okay, the meaning of this is, then what is the meaning of this? Guys, the meaning of this is when cache is full, let me write here. Let me write here one by one. So when cache is full, you are going to use LRU. And when you are adding, okay, new data needs space. Okay, you can use LRU. And when Spark removes the RDD partition that have not been used recently. So in these three cases, you can use this LRU. But sometimes you want manual controls, guys. See here, next point, I'm saying you the same thing. Okay, but sometimes you want manual control, especially in long running jobs. Okay, so for that, Spark provides rdd.upPersist.method. Okay, so this immediately removes the cached RDD from memory or from the disk. So very useful. This is very much useful in what? Iterative pipelines where earlier stages are no longer required. And you just imagine, guys, for diagrammatic interpretation, I'm telling you one thing. So think of Spark cache as a bookshelf where older books are removed automatically, but you can decide to manually remove a book when you no longer need it. Okay, so you have to understand this. So now I think you're all in a position to answer this question. What policy does Spark use for eviction? So it is using LRU. Okay, so now that we have covered caching and persistence, so now let's move into performance considerations for machine learning workloads. So I'm talking about MLlib now. Guys, Spark is widely used for ML. So the natural question becomes, so how do we optimize machine learning pipelines in Spark? Okay, so this slide is completely explaining or outlining several important considerations. So I'm naming this as one by one. So let me take the very first one, that is preparing features. So guys, this is the most important stage. So this is the most important stage. Good features matters more than the choice of algorithm. See, feature scaling, text processing, and clean labels drastically boost model quality. Okay. And what is the second one? The second thing is called as configuring algorithms. Guys, regularization often improves accuracy by preventing overfitting. So don't rely blindly on default hyperparameters, guys. So always I would request you to what explore variates. So that will be what happening in second level. And what is the third one? Caching RDDs reuse. Guys, ML algorithms are iterative. Remember this. And also we all know that. So they pass over the same data set multiple times. So caching the training data is critical for speed. Okay. And what is the fourth one? Recognizing sparsity. Sparsity means what? Sparse means no data. Check your feature. See, check your feature. Vectors are mostly zeros. See, suppose you have an array. So in this array, instead of having what integer value, you have 0. Okay, this is called as sparsity, right? So what you have to do first? So you have to check your feature vectors are mostly zeros. Okay, so in that situation, using sparse format saves space and time. And finally, we have level of parallelism. So always ensure enough partitions, at least as many as cores, guys. Okay, suppose you have 8 core systems, so then you do 8 partitions. You have 12 cores means you do 12 partitions. But too many partition increases communication overhead. So keep this point in your mind. So these principles make ML pipelines for smoother, faster, and more scalable. Okay. Guys, we have just seen algorithm level optimization. So next we will be what move to the hardware side. So how to provision and how to tune your cluster for peak Spark performance. So let's start with the hardware part. So we are mentioning it as preparing features. Guys, so you all know, right? So we have just seen a list of ML performance principles. So now let's dig a bit deeper. So here's the question to frame to this slide is, so why do some ML models perform beautifully while others fail miserably? So even with the same algorithm. Guys, here you can find a what solution to it. So this complete slide reinforces a critical truth of machine learning. Okay. Your model is only as good as your features, guys. See, you all know, right? Many ML beginners spend all their time picking algorithms. But what experienced data scientists will do, guys? Experienced data scientists know the feature engineering has a far larger impact. So here we have some best practices, guys. So the best practices include adding more informative features. Okay. Adding more informative features. Guys, if your raw data is not impressive enough, your model simply cannot learn. So adding domain-driven signals often improves accuracy drastically. That you should have it. And the second one is, the second very, very important point is scaling features. Scale your features. Guys, for distance-based algorithms or gradient-based optimizers, so scaling prevents some features from dominating others. Okay. And third one is featurize text correctly or featurizing text properly. Guys, text must be tokenized. Text must be cleaned. Text must be converted into vectors. Remember this. So what I would like to say here is text must be tokenized, cleaned, and converted into vectors. So often using libraries like NLTK, or we have some inbuilt functions inside Spark. So Spark built-in transformer also you can use to what? Convert this into tokens, cleaned, and also converted vectors. Okay. And finally, the last one is label classes correctly. Guys, model quality depends heavily on correct labels. Okay. So even subtle mislabeling can ruin accuracy. So maybe you have heard about feature engineering, correct? No. So feature engineering, therefore, is not an optional. So it is the core of machine learning performance. Understanding? So what you have understood now? So now that features are prepared, so now let's consider algorithm configurations. So how we are going to configuring the algorithm? See, once we have good at features, the next questions becomes how do we tune the algorithm itself? So here I'm giving you the complete information. So here this slide is emphasizing that Spark ML algorithms can be sensitive to hyperparameters. So especially regularization parameters. The very first point what I would like to highlight here is why regularization matters. Why regularization matters, guys? See, models often learn noise or irrelevant patterns from the training data. Correct? No. So regularizations adds a penalty to overlay complex model and encouraging simplicity and reducing overfitting. Okay. So here I've given that point. Regularization avoids overfitting by making models simpler, penalizing large coefficients, etc. And one more very important point, what I would like to say here is don't rely only on defaults. Don't rely only on defaults. Guys, default hyperparameters are decent, but not perfect. Correct? No? So trying a few different values, such as adjusting regularization strength, learning rate, max iteration. See, all these can significantly improve the accuracy. And along with that, always evaluate changes on test data. This is the last point I'm telling you. So it is easy to tune your model to look perfectly on training data. See, only to fail in production, but validation and test sets helps to avoid these traps. So algorithm configuration is really about balance, not too simple, not too complex. So now tell me, guys, which is worst? Overfitting is worst or underfitting is worst? Huh? Overfitting or underfitting? So which is worse? Overfitting, right? So overfitting is usually the bigger enemy in real application. Remember this. Okay. Now, so let's reinforce why caching and sparsity matters so much for ML workloads. So here I have mentioned this as a other tips. So this slide is giving you the several very practical tips, guys. The very first one, I'm mentioning this as caching RDD to use, or you can call it as caching data sets. Guys, ML library algorithms are iterative. That we all know. So meaning of this is they pass over the data set multiple times. Okay, that you have understood already. And caching the data set before training makes iteration extremely fast. And third point is if data does not fit in memory, persisting to disk is the fallback. Clear? So this is the first tips I'm giving you here. And the second tip is recognizing sparsity. Already I've told you about sparse. So if most values in your vectors are 0, then you have to use sparse vectors. Remember this. And this drastically reduces memory usage and speeds up computations. So this is the second tips I'm giving to you all, guys. And the third tip is, so use level of parallelism. So you should have at least as many partitions as CPU cores. Already I've told you, right? Otherwise, some cores will sit idle and slowing your job. And conversely, too many partitions can increase shuffle overhead. Remember this. So already I've told you about shuffle overhead also. So you have to parallelly take care of that also. And you must strike a balance. So usually a few hundred partitions for larger job. That is enough. Understanding, guys? So these are all tips I'm giving to you all, guys. So we have tuned ML jobs now. So now let's step back and talk about hardware level optimization. So this is hardware level optimizations, guys. So we have optimized the software side. So the next logical question is, so how do we choose the right hardware setup for Spark clusters? So here I'm completely explaining I'm completely listing extremely useful production level guidelines. Okay, the very first one I have mentioned here as run closer to data. Run close to data. Guys, if you use HDFS, okay, so keep Spark workers on the same network. So ideally on the what? Same node. So minimizing data movement is the key here. So hope everyone understood this point. Okay. And the second one is storage. Second one is storage. So this is the another production level guidelines I'm giving you all, guys. So use 4 to 8 disk per node. Guys, each disk should be mounted separately. No RAID concept for maximum parallel throughput. And the third one is memory sizing. This is another very, very important one. Guys, a node should ideally have 8 GB or more memory. But large memory machines like greater than, let me take greater than 200 GB. Okay, so that must run multiple executors for efficiency. Okay, and next one is network. Okay, next one is network considerations. And before that network considerations, so we have to think about one more thing, guys. So memory usage, we have to check in Spark UI. Okay, memory usage, we have to check in Spark UI. Guys, load your typical data set and inspect how much memory an RDD takes. So this is very, very important one, guys. Okay, so this helps you to allocate executors and memory precisely. And after that, we are going with network concept. So network considerations. So shuffle heavy jobs benefits from 10 Gbps or more network speed. And finally, we have CPU cores. So aim for at least 8 to 16 cores per machine. Okay, so Spark is heavily CPU bound once data is cached. So these tips help you to what ensure the cluster balances CPU, disk, memory, and network optimally. I hope this hardware thing is crystal clear to everyone. So my last question to you all is, so which is usually the biggest bottleneck for shuffle heavy jobs? Which is the biggest bottleneck? Can anyone answer? Is it network or CPU or memory? Obviously network, right? So network is often the real bottleneck. So with the hardware tuning covered, so we are completing the today's session, guys. And also here we have given a link. You can go with this link. So this link will give you the Spark hardware provisioning doc. So if you want to learn more about this means, you can go with this link. So that's all from my end, guys. And the next slide, I have given few post midsem topics review. So this is not given by me. So this is given by the main what author. So I'm giving you just like it, guys. So that's all from my end. So we have covered massive amounts of ground today. So we have started from streaming architecture and we have ended Spark streaming. So we have learned structured streaming, performance tuning, and hardware provisioning. Now the question to you all is, so how do we bring all of this together? So how do we bring all of this together? You think on that, guys. Yes, that's all from my end, guys. So this will complete your 16th session concept. So we have reserved last 3 sessions for Spark. And finally, I would like to congratulate everyone. So this was the dense and technical session, and you handled it very well. Yes, any questions? Pradeep, no question bank. There is no question bank and there is no previous year question paper. So this is first time I'm taking course for you people. Already you have seen my makeup examinations questions, right? The same way you'll be having in comprehensive exam also. So 40% I'm taking from 1 to 8 session and 60% I'm taking from post midsem. Tanya, actually the data frame topic is missing and also page number from 118 to 122. See, that is come to my notice also. But right now I have distributed what the slides to you people, because see, I have not checked with that. That is from my end only. That is the mistakes from my end only. So anyway, you have gone through the concept in recorded video, right? You just go through that. Okay. Yes, 1 to 8 session 40% and 9 to 16 60%. Correct. Seni. So actually, I did not notice that, Tanya. Now I can't do anything. Sir, we are going to get the same level of questions as EC2 in EC3. Yes. Yes. Since it is open book exam, you just imagine. Okay. Yes, of course. Yes, of course. Guys, uh, almost all the concept what I've taught in the theory, I'm going to give you in the examinations. So even you will be having queries also. But little bit what your mind you have to use there, guys. Brain you have to use in examinations. Yeah, it is huge syllabus, Jyoti. So this is not set by me. So here there is a author, right? So he is the course owner. But I think you people got very good knowledge, right, on big data. Yes or no? See, the complete ecosystem they have covered in the entire syllabus. Correct? No? Even I felt very happy. So after seeing all these PPTs. The same course I'm taking for next batch also, means DSC batch also. Some little bit modifications we have done there. That's it. So some shuffling we have done in the new one. Sir, assignment was cover most of the Hadoop and big data syllabus. Correct. Tanya, actually, we have taken all the submitted assignments from mail, submitted assignment from your MS stream, MS what team, and also from Taxila. So no need to worry on that. So even you people will get your marks soon. So that's why I told you to put CC to me. I think you all send your assignment to Kamlendra sir, right? So he started evaluation and maybe today he is going to finish. So today he has to enter everything into Taxila. So after entering marks, I will cross check once. Once everything is ready, then I will ask higher ups to release the results. Yes, no problem, Gautam. So we have taken from all these sources. Okay, we have taken from Taxila. So we have taken from mail. We have taken from MST. Samanvita, complex or basic? Very basic, not complex. That is depends on you people, right? Complexity and basic, that you people have to tell. Okay, any other questions? Okay, guys, we have left with 8 more minutes. So if you want to convey any messages at the end, please do convey, guys. I have 25 students. So how was the entire journey? One by one, can anyone unmute yourself and can you tell me? How was the entire journey of BDS? Tanya, Ravi Kumar, Niklesh.
Sir, it was very informative. We learned many new things as it was not my domain, but I still learned many new things here, many new concepts. And, like a new opening for me, new horizon is open.
So how about my teaching?
Yeah, it was very good.
Okay.
Yes, sir. In addition to that, it's really very informative and lot of new things. We might be we know everything in bits and pieces, but we never have had a chance to correlate all these things. Like just we learn the Hadoop. It's like ecosystems. In Hadoop, we have to integrate everything. We know the scripting, but we are not using that knowledge to consolidate and prepare one ecosystem where everything is coming up. Kafka, SDFS, Spark, every tools is coming up. It's quite lengthy, but yeah, we got a gist of it, and I think we need to start exploring those things in our project.
So usually, Ajit, any courses will trigger you people to start with the framework, right?
Yes.
So even we have started with that. So we have triggered you people. So now onwards, you people have to use the tools in future.
Yes. Yeah.
Okay, that job we have done. See, whatever the theoretical concept is required, that we have given in the entire course. Yes, Tanya, you have raised your hand.
So, sir, learned so many tools together, quite informative sessions, and your teaching was flawless. Even assignments were, we learned something practical and hands on kind of a thing.
Okay, thank you, Tanya. Yes, Monish.
Yeah, hi sir. So apart from what we have just mentioned, all of us, the thing is, I am having 20 plus of year experience in IT actually. So, but I am always in IT and in cloud computing domain. So I could
Mm,
say after going through the Hadoop and big data courses, I can go and work in a big data project. So that's a new horizon or new that things comes up actually, and that has opened for me for the future. Yeah,
thank you, Monish.
definitely it's very good, very awesome.
Thank you,
Thank
Sunny.
you.
Yes, Gautam.
Yes, sir. I found the course and the topics very new and very exploring for me, and I'm really looking forward to utilize in my, I mean, day-to-day work. Sometime whenever there is a scope, even I can suggest others also. If somebody is struggling with big data, even already I see in our, I mean, work also where chances are there to shift them into some big data system. And
So,
overall, I see, I found that your energy level while teaching is really great, sir. So I'll also, as a student, will like to adhere to that because that also needed.
Gautam, do you know today this is my third class? So, this is my sixth hour. So, with the same energy, I'm teaching.
Yeah, I saw it from the very first class. Your energy level is same. Yeah.
Thank you, Gautam. Yes, Jyoti. Jyoti, you can unmute and you can convey your message.
Hello.
Yes, Jyoti.
Yes, sir. Actually, your way of teaching big data concepts make everything crystal clear, and basically, it's very complex job to me because I'm from network and security background.
Mm,
So I'm understanding each Hadoop concepts and big data concepts is quite fair to me. So you make complex technologies like Spark, Kafka, and Hadoop feel very simple. And your
mm.
big data sessions always make me think deeper and learn smarter. So thank you so much, sir. Yep.
Now, is it become very easy, Jyoti?
Uh,
Now, tell me
yeah,
how
yeah.
many, how you are familiar with how many tools after completion of this BDS?
Approx all tools like Spark, Kafka, most of the technologies, yeah, I'm quite familiar. So,
Mm.
yeah. So, thank you for explaining, large scale systems with such clarity and patience. So, and yeah,
It's
thanks.
my job, Jyoti.
Thank you so much, sir.
Thank you,
One
Jyoti.
thing, one thing I would suggest, maybe next batches, whoever, we
Mm.
can little bit reduce the introductory part, maybe shorten, and those and we can save more, little bit one or more session on more practical one. It can
Gautam,
be,
Gautam, 1 second. Uh, you are in first semester, right?
yes, yes.
See, actually, the same course we have introduced in third semester.
Okay.
See, in third semester, uh, see, we have reduced some syllabus because so we have taught cost subject in first semester, and the continuation of
Mhm.
that is BDS year. But for you people, so this is the first course, correct? No,
Mhm.
without having basics. See, that's why we have introduced so many fundamental concepts in first 3 to 4 sessions. Okay.
Yeah, I saw that. Yeah, first
So
three. Yeah,
without
initially.
understanding cache coherence concept, now you are all understanding, right? So every time we are talking about architecture. So
No,
that's
sir,
why we have
that
introduced
is,
so
I
many
think
introductions.
course is fine. I mean, this time I saw we are short of month also. I believe that was everybody will agree. Otherwise, with that, whatever course and with the full stretch of 6 months, it is fine. But
Mhm.
this time we got less time. That's the problem for, I mean, most of us will be.
Definitely, I will consider your
Yeah.
suggestions, Gautam.
If the time is short, I think we can see somewhere how to, I mean, shorten and yeah. Otherwise, full 6 month, whatever the course structure, it's really good. Yeah.
Yeah,
And
definitely,
it's
I
up to
will
the market. Yeah, up to
talk
the,
to the
yeah.
course owner and I will suggest him to reduce the content.
Yes, sir, I agree with that too.
Sure, Jyoti, I'll do that.
And sir, in addition to that, everything looks fine. One more thing, if we can focus more towards the practical, like too much, too much theory, and maybe I think we can introduce some part in the practical marks.
Ajit,
Because
see, regarding this, one thing I would like to tell you. See, for next batch onwards, we'll introduce webinar concept.
yes,
Okay, so we will be having 4 webinars. So in 4 webinars, we will try to cover practical things.
yes, that's going to help more than going
Correct.
through all this theory. And
Actually, in cluster, we are doing the same, Ajit. But here, you people have only one section, right? So one
Yeah.
section for 4 webinar, it is little bit difficult. Okay, 4 webinars has to be done by one LF, right? One learning facilitator. So that is the difficult part. So definitely, even I will take these considerations next onwards. So I will try to introduce webinar to you people.
yes, yes.
Okay. Yes, the next again, one more CC batch is starting on January. So I will plan to introduce the webinar there. So there I will focus more on practical things. Thank you, Ajit. Thank you for your wonderful suggestion.
Yeah, thank you. Thank you. I think overall it's a really good experience and good learning. Thank you for all your supports and energy level to taught us all these things.
And even I thankful to you people, guys, because see, now also today also I got 25 students. So in many classes only 4 or 5 students are attending, but in my class I have seen mass of students. So this is great. And yes, guys, at the end, all the very best for your upcoming comprehensive open book examination. So may your hard work, dedication, and consistent learning guide you smoothly through even every questions. Stay calm, stay confident, and trust the knowledge you have built over the months. And you have got everything it takes to excel. So go ahead, guys. So give it your best. So wishing you success and brilliant performance. So all the very best, guys. So thank you all. Thank you for your cooperations in the entire
Thank you,
16
sir.
session.
Thank you, sir. Bye-bye. Bye.